The components of piston engines are subjected to high loads, high temperatures and high speeds. As the components move against each other, a force is generated which resists their movement. This force is called friction. The friction produced will increase as the load on the components, their temperature and the speed at which they are rubbing together increases. The fact that the components rub together also produces wear, which causes the partial loss or destruction of the metal components. Both friction and wear can be reduced by preventing the moving surfaces coming into contact with each other, by separating them with a substance which has lower frictional properties than the component parts. This substance is referred to as a lubricant. Aircraft piston engines use oil as a lubricant. The oil also performs a number of secondary functions, and in this lesson we will look at the functions that the oil accomplishes. We will list the methods used for lubricating the moving parts of an engine with oil, and we will examine the two types of oil system in common use. The primary task of the lubrication system of the engine is to reduce friction and component wear. As we have said, it also has a number of secondary functions. Of these secondary functions of the lubrication system, perhaps the most important is the task of cooling. The flow of oil through the engine helps to remove the heat from the internal components of the engine. This heat can then be dissipated in a radiator or oil cooler, which must be exposed to the cooling effect of the air flowing past or through the engine cowlings. As the oil flows through the engine, it also carries away unwanted foreign particles and also the byproducts of the combustion process, such as carbon, which forms on the piston crown. These deposits are strained out of the oil by the oil filter. Thus, the oil can be said to clean the engine. The internal metal components are protected against corrosion by the lubricant, a thin film of which tends to stick to the metal surfaces. The oil can act as a hydraulic medium. It can be used for this function in two ways. Firstly, it can provide the hydraulic power source for the operation of various components on the engine, such as a variable pitch propeller. Operation of the variable pitch propeller is fully explained in the lesson on propellers. Secondly, it also acts as a hydraulic shock absorber, reducing the shock loading between the shafts and bearings in the engine, thus reducing vibration. The oil system's use as an indicating medium is of great importance to the pilot, as it can give an early warning of impending mechanical failure or loss of power. The lubricant can be used to show the condition of the engine, both in terms of oil temperature and oil pressure. On some engines, the oil can also be used in a torque meter to indicate the power being developed. Operation of the hydraulic torque meter is fully explained in the lesson on propellers. There are three methods of lubricating the moving parts of an aircraft piston engine with oil. They are the pressure system, which has a high-pressure oil pump incorporated in the design, which supplies oil under pressure for lubrication of the major components. The splash system, where oil is thrown onto the major components by the rotation of the crankshaft in the oil sump. And the combination pressure splash system, whereby the major components are supplied by pressure oil from a pump, and the remaining components are supplied by splash lubrication. Most modern generation engines use the combination pressure splash method. There are two different types of lubrication system in common use in aircraft engines. They are the wet sump and dry sump systems. The main difference between the two systems is the method which is used to store the supply of oil. Most light, non-aerobatic aircraft engines use the wet sump system. In this system, the oil is stored in the bottom or sump of the engine. This method simplifies the construction of the engine, but it has a number of disadvantages. The first of these disadvantages is that lubrication difficulties arise during aircraft manoeuvres. The oil enters the crankcase, where it is flung around by the revolving shafts, possibly causing both over- and under-oiling of the engine. Inverted flight being a particularly hazardous undertaking for the wet sump engine. As it is stored within the hot engine casing, the temperature of the oil is difficult to control. Because of the continual contact of the oil with the hot engine, the oil becomes contaminated and breaks down. It can also combine with some of the free oxygen remaining from the combustion products or oxidize more easily. Finally, the oil supply is limited by the sump capacity. The dry sump system overcomes the problems of the wet sump system by storing the oil in a separate remotely mounted tank. However, this type of system does have the disadvantages of being heavier and more complex. The principle of oil supply is the same for both wet and dry sump systems. Both use the combination method of pressure and splash lubrication, after which the oil is returned to the engine sump by gravity. In a dry sump system, however, one or more scavenge pumps return the oil from the sump to the tank to prevent flooding of the engine sump. That is the end of the lesson. A list of the primary and secondary functions of the lubrication system is being displayed on the screen. Study these carefully before moving on to view the advantages and disadvantages of wet and dry sump lubrication systems. In the wet sump lubrication system, oil is stored in the sump at the bottom of the engine. In the dry sump system, the oil is stored in a separate tank. Make sure you are fully conversant with the advantages and disadvantages of the two types of system before you leave the lesson. The principal units in a typical reciprocating engine oil system include oil filters, a pressure pump, an oil cooler, oil pressure and temperature gauges, plus the necessary interconnecting oil lines, and in the dry sump engine, an oil tank, and a scavenge pump or pumps. All of these components are shown here. This diagram illustrates a dry sump system. Remember, the oil tank and scavenge pump are not necessary in a wet sump system. In this lesson, we will have a look at each of the components in detail, beginning with the oil tank. Oil tanks are made of sheet metal. They are fitted with baffles and strengthened internally to prevent damage due to the oil surging during aircraft maneuvers. The tank is placed, whenever possible, at a higher level than the engine to enable a gravity feed to the pressure pump. The tank forms a reservoir of oil, large enough for the engine's requirements, plus an airspace. The airspace is necessary to cater for several situations. When, after a run, the engine is stopped, the walls of the crankcase are saturated with oil, which will drain into the sump. The oil will remain there until the engine is started, when the scavenge pump will return it to the tank. As the oil absorbs heat from the bearings, it expands, necessitating a greater volume of space than when the oil is cold. The oil becomes impregnated with bubbles of air as the engine components throw it about. This aeration causes the oil to froth, which greatly increases its volume. Another reason why the airspace is necessary is the fact that oil can be displaced from the variable pitch propeller and any other automatic controlling devices when they are used. Scavenge oil from the engine sump is passed over a de-aerator plate to the inside of the hot pot. The plate allows the bubbles of air to escape from the oil, thus reducing frothing. The oil tank is vented through the crankcase breather to maintain the pressure on top of the oil equal to the atmosphere in order to prevent oil losses during excessive frothing conditions. The hot well or hot pot forms a separate compartment within the oil tank. Its purpose is to reduce the time taken to raise the temperature of the oil when starting the engine from cold, by restricting the quantity of oil in circulation when the oil is cold and viscous. The hot pot consists of a cylinder of metal with holes cut in it, fitted above the oil outlet to the engine. The oil must pass through the hot pot to reach the pressure pump. During engine start, the level of oil in the hot pot drops as it is taken into the engine. This uncovers a ring of small diameter ports which are cut in the wall of the hot pot. These ports offer a high resistance to the flow of cold, thick oil, so that very little of it passes into the hot pot to join the oil going to the pressure pump. This means that when the oil is cold, only the oil contained within the hot pot is in circulation. This limited amount of oil warms up rapidly. The hot oil raises the temperature of the walls of the hot pot. The oil in the immediate vicinity outside of the walls of the hot pot is also heated and becomes less viscous as a consequence, so that the ports offer less resistance to its flow and progressively more and more oil is brought into circulation. If a feathering propeller is fitted to the engine, the lower ring of feed ports in the hot pot are placed above the bottom of the tank. This provides a feathering reserve of oil, even if the main tank has been emptied through the normal outlet, as may occur if the main feed pipeline was to develop a leak or completely fail. A coarse metal gauze filter, known as a suction filter, is fitted between the tank and pressure pump. It is designed to remove particles of contaminant from the oil before it enters the pressure pump, and so prevent damage to the pressure pump. The oil pressure pump consists of two deep tooth spur gears which are rotating inside a close-fitting pump casing. It is fitted to the engine accessory housing and is mechanically driven by the engine. Oil is carried on both sides of the casing in the spaces between the gear teeth and is made to flow as the gears rotate. The restriction to flow is generated by the tolerance fit of the engine components to be lubricated. This enables a rise in system pressure. The actual oil pressure obtained will depend on the speed of the pump. The temperature of the oil, and the resistance offered by the tolerance with which the components fit each other. The capacity of the pressure pump must be such that it will supply a minimum oil pressure under its most adverse running conditions, which are those of low rotational speed and high inlet oil temperature. Because the pump is capable of supplying such a large quantity of oil under these poor conditions, under normal running conditions the increased flow then available would tend to generate a dangerously high oil pressure. Very high oil pressures are prevented by a pressure relief valve which is fitted across the pump inlet and outlet connections. This limits the maximum oil pressure in the system. The valve consists of a ball sealing an orifice. The ball is held in the closed position by a spring of suitable strength. When the oil pressure reaches a predetermined figure, it overcomes the spring and the valve opens, allowing sufficient oil to return to the inlet side of the pump to control the oil pressure at that figure. The pressure relief valve maintains the oil pressure more or less constant, regardless of engine speed or oil temperature. The pressure filter is fitted downstream of the pressure pump. It is usually of the paper element type and is designed to remove very small solid particles before the oil passes to the bearing surfaces. This filter will also protect the engine if the pressure pump breaks up. As shown here, on some filters a spring-loaded relief valve is fitted to bypass the filter element when the oil is cold, or if the element becomes blocked. The oil tank will usually be fitted at a higher level than the pressure pump to provide a gravity feed. When, after an engine run, the engine is stopped and the oil is hot and thin, the force of gravity will generate sufficient pressure in the pressure pump feed line to force the oil through the clearances in the pressure pump. This would result in the oil tank draining into the crankcase, and as a consequence the engine may be flooded with oil. This sometimes is referred to as over-oiling. To prevent this occurring, a check valve is fitted in the outlet line to the pressure pump. This consists of either a lightly spring-loaded or a solenoid-operated valve which will retain the oil in the tank until the engine is started. On engine start, suction from the pressure pump will pull the valve off its seat and the oil will be allowed to flow freely. The scavenge pump, or in some engines the scavenge pumps, pump the oil from the sump back to the tank. Scavenge pumps are of the same pump type as pressure pumps and are also mechanically driven from the engine's accessory gearbox. When the engine is stopped, the oil which remains in the crankcase will drain down into the sump. As the engine is started, there will be a quantity of oil which, if the pressure and scavenge pumps were of equal capacity, would not be removed. Therefore, in order to prevent excessive accumulation of oil in the sump, it is necessary for the scavenge pump to be of a larger volumetric capacity than the pressure pump. In practice, the scavenge pump capacity is 25 to 50% larger than that of the pressure pump. To protect the scavenge pump from being damaged by large pieces of debris, which may have passed through the oil system, a coarse metal gauze filter is fitted over the oil outlet pipe within the sump. The importance of the use of oil to cool the internal components of the engine has already been emphasised. If the oil itself gets too hot, it may be unable to fulfill its task as a lubricant. To prevent the temperature of the oil getting too high, an oil cooler may be fitted. Because of their high engine temperatures, diesel aero engines always have oil coolers. In its simplest form, an engine oil cooler is made up as a matrix or tube block, similar to a bunch of drinking straws which have been clamped together. Ram air flows through the inside of the tubes in the block. The oil is allowed to flow between the outer surfaces of the tubes, which are separated by dimples formed in their centre sections. The oil is spread in a thin film which flows through the inner surface of the matrix. When the engine is started from cold, the oil cooler will be full of cold, thick oil, and to force the oil through the small passages within the cooler would build up a very high oil pressure. To prevent this high oil pressure damaging the oil cooler, a pressure-operated anti-surge valve is fitted, which allows the oil to bypass the matrix when the oil is cold. The temperature of the oil is affected by three factors. Firstly, the amount of heat generated in the engine, which is proportional to engine power output. Secondly, the temperature of the cooling air. And thirdly, the rate at which the air flows through the oil cooler. In some light aircraft, the flow of air through the cooler is simply dependent on the forward speed of the aircraft in flight, and the airflow from the propeller whilst the aircraft is on the ground. In certain conditions of flight, where high power is used with low forward speed, for example during a climb, care must be taken to prevent overheating the oil. The aircraft flight manual will recommend climb speeds that should ensure adequate airflow over the cooling systems. Higher powered aircraft will be fitted with shutters to control the flow of air through the cooler. The shutters will be closed at startup to allow the engine oil temperature to rise quickly, and then be opened to maintain the temperature. In flight, the shutters will be closed off again as the temperature of the air reduces at altitude. Control of the shutters can be manual or automatic. The parameters of the oil system which are monitored are oil pressure, oil temperature, and oil quantity. The temperature of the oil in an aircraft piston engine may be measured at the outlet from the oil cooler, or at any position between the oil tank and the inlet to the engine. On the majority of wet sump systems, the oil temperature is measured at the pressure filter housing. Most aircraft use an electrical sensor to indicate the temperature on a cockpit instrument. Temperatures in the region of 85 degrees Celsius would be considered normal. Oil pressure is sensed at the outlet side of the engine-driven pressure pump. The sensor can be either electrical or a direct reading mechanical system. The operation of both the oil pressure and oil temperature gauge is fully explained in the engine instruments lesson. It is mandatory that oil temperature and oil pressure are indicated on the flight deck. Oil quantity may be shown in the cockpit, but if it is not, then there will be a facility for checking the quantity prior to flight, either by the use of a sight glass on the tank or a dipstick. A dipstick is a metal rod inserted into the tank. It is calibrated to show the level of oil in the tank as a wet area when it is removed. Because aircraft engines operate at varying loads, power settings and outside air temperatures, their lubricants require differing properties. In this lesson, we will examine the properties required of aero piston engine oils and we will look at the types of oil available. The thickness or viscosity of an oil is a very important factor. Viscosity is defined as the measure of a fluid's internal friction or its resistance to flow. A liquid that flows freely has a low viscosity, thin oil, and one which is sluggish has a high viscosity, thick oil. The viscosity of an oil will change with changes in temperature. An increase in temperature will reduce an oil's viscosity and vice versa. The engine's operating temperature will vary considerably from the time when it is started from cold to when it has been running at high power for long periods of time. The oil's viscosity must stay within required limits to do its job. The viscosity of the oil used in aero engines does not change a great deal over its normal operating range. There are various standards employed to determine the viscosity or thickness of oils. They all provide a datum by which differing oils can be compared. Obtaining these standards require that we measure the time taken for a fixed quantity of oil at a given temperature to flow through an orifice or jet of a given size. The standard that is generally employed in aviation to indicate the viscosity of oils is the Society of Automotive Engineers or SAE grading system. This system uses numbers to indicate the viscosity or the grade of the oil. However, some oil companies still use an old grading system known as the Seybolt Universal Second System to grade their oils. You can see from the chart that the SAE grade number is approximately half of the equivalent Seybolt Universal Second number. The lower the viscosity grade number, the thinner is the oil. And the higher the grade numbers, the thicker the oil. The air temperature in which the engine operates has an influence on the viscosity of the oil selected for use in that engine. For example, a light aircraft operating within the United Kingdom during the winter may use SAE 40 grade oil, and in summer it might use 50 grade, the choice of the grade being dependent on the average ambient temperature. The use of an oil with a single viscosity grade can cause problems with it either being too thick when it is cold, causing problems with engine starting, or with it being too thin when hot, leading to insufficient lubrication. To solve these problems, multi-grade oils can be used. These oils have two viscosity grades, one for when the oil is cold and another for when it is hot. For instance, SAE 15W50 oil will act as 15 grade oil, a thin oil, when it is cold, and as 50 grade, a thick oil, when hot. The W indicates that the oil is suitable for use in winter in cold climates. The type of oil used in aircraft piston engines is normally mineral-based, that is to say that it is produced from crude oil. However, some engine manufacturers have trialled and approved the use of semi-synthetic oils. Synthetic oils are lubricants consisting of chemical compounds which are artificially made from material other than crude oil. If the oil contains no additives, it is known as a straight oil. Generally, straight oils are only used when running in new engines or for specific engine installations. To meet certain requirements of engine operation, additives can be mixed with the oil. These additives can take the form of antioxidants, dispersants, and oiliness agents. Oils which contain additives are called compound oils. Straight and compound oils are both identified by the viscosity numbering system. But a compound oil will have additional lettering in front of the number to indicate the types of additive. Thus, a bottle or can containing a straight oil with a viscosity of SAE 50 may have only the number 100 marked on it. But a compound oil of the same viscosity will be marked with a letter or letters followed by the number. The actual lettering code used varies with the oil's manufacturer. In this particular case, the letters AD denote that the oil is an ashless dispersant oil. That is to say that the oil produces no ash and it contains an additive which suspends contamination in the oil and allows it to be carried away. That is the end of the lesson. Here is a summary of the main points. Viscosity is defined as the measure of a fluid's internal friction, or its resistance to flow. A liquid that flows freely has a low viscosity, and one which is sluggish has a high viscosity. An increase in temperature will reduce an oil's viscosity, and vice versa. The lower the viscosity grade of an oil, the thinner the oil is. And the higher the grade number, the thicker the oil is. Oil containing no additives is known as straight oil. Oil which contains additives is called compound oil. Indications of oil pressure and temperature give the pilot a good idea of the mechanical integrity of the engine. Of course, the pilot must then interpret these indications correctly. In this lesson, we will examine the meaning of some of the indications the pilot might see on his instruments. We will state when the oil quantity should be checked, and we will look at the phenomena known as hydraulicking and coring. After starting an aircraft piston engine, positive engine oil pressure should be indicated within a specified time. The Piper Warrior checklist stipulates 30 seconds. If oil pressure is not indicated within the specified time, the engine must be shut down immediately and the problem investigated. If the engine is started from cold, initially the oil pressure could appear to be excessively high. This indication can be considered to be normal, as long as the pressure drops to within its normal range as the engine warms up. Correct engine operating pressures and temperatures are dependent on each other. If the pressure fails to drop back to normal or rises to a dangerously high value, the engine must be stopped to prevent damage. The oil pressure should be within its operating range at the correct operating temperature. High oil temperature could cause the pressure indication to be low by causing the viscosity of the oil to drop too low. If the engine is fitted with oil cooler shutters, they can be opened in an attempt to lower the oil temperature. Alternatively, if oil cooler shutters are not an option, then consideration should be given to attempting to cool the engine and thus the oil by either reducing engine power or lowering the nose of the aircraft to increase airspeed without increasing power, or even making the mixture richer. If the oil temperature is within its correct operating range and the oil pressure is still indicating that it is too low, then it is likely that there is excessive clearance on the bearings due to wear, a defective pressure relief valve, or potentially, even worse, leaks from the output side of the pressure pump. If the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage being caused to it through lack of lubrication. Fluctuations in oil pressure could be the result of either low oil levels or system faults. Small fluctuations of the oil pressure gauge needle, either side of the desired pressure, may be indicative of a sticking pressure relief valve. This will cause the pressure to first build up beyond the optimum level, then subsequently, when the pressure reaches a point high enough to overcome the stiction of the valve, it will open, dropping the pressure momentarily below the correct level, then the cycle will start again. Large fluctuations of the oil pressure gauge needle, on the other hand, will probably be caused by insufficient oil in the system. The engine may have been leaking oil and eventually the level will drop to a point where the pressure pump cannot sustain its output. Then the pressure will drop momentarily until the pump can get some more oil, when the pressure will rise again, if only for a moment. If the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage. If the oil pressure falls suddenly to zero, the probable cause is either failure of the pressure pump or a total loss of oil. The engine must be stopped to prevent further damage. A problem that can occur during starting in very cold weather is coring. It is caused by the fact that the very cold oil does not flow correctly through the oil cooler. The cooler matrix may be blocked by the very viscous cold oil. On coolers with a bypass valve, the only oil flowing in the system will be that flowing through the bypass valve. In systems without a bypass valve, a thin core of hot oil will pass through the cooler, but the oil at the outer extremities will remain very cold and viscous. In both systems, the temperature of this oil will rise very quickly, and there will be a great temptation to open the oil cooler shutters. However, this will make matters worse by further cooling the oil blocking the cooler. The only solution to this problem is to close the oil cooler shutters and allow the oil in the cooler to warm sufficiently for the flow of oil to return to normal. It should be appreciated that as the oil is used to lubricate the moving parts of the engine, it will come in contact with the combustion gases. The inlet and exhaust valves and piston rings do not have a 100% seal, and as a result, some oil will be burnt and the engine will therefore have an oil consumption rate. A typical light aircraft engine would use around 1 pint or 0.56 litres per hour. A consumption rate greater than the recommended limit may be an indication of engine wear. The Lycoming engine used in the Warrior training aircraft is an American engine. Its maximum oil consumption rate is 1 US quart per hour. If the engine has a dry sump lubrication system, the oil tank contents should be checked immediately after the engine has stopped, realistically within a few minutes after shutdown. This ensures that the contents are recorded accurately before the oil migrates, under gravity, down into the engine sump. As explained in a previous lesson, some engines have a check valve which prevents this migration. The wet sump system requires the opposite treatment. A period of at least 15 to 20 minutes should have elapsed after the engine shut down, before the contents are checked by using the dipstick in the engine sump. With both systems, a period of time will have elapsed after engine shutdown before the oil level is checked, albeit in the dry sump system, a very short period. The piston engine is a heat engine. Its purpose is to convert the heat energy released by the fuel into mechanical energy and so allow it to do useful work. We have already said in a previous lesson that the thermal efficiency of a piston engine is at best only 25 to 28%. This means that over 70% of the heat energy released by the fuel in the engine is wasted. The exhaust gas is responsible for releasing around 40% of the heat energy. On some aircraft, some of the energy lost through the exhaust can be recovered by using it to drive a turbine-driven supercharger, which is commonly called a turbocharger. Operation of the turbocharger is covered in a later lesson. The remaining approximately 32% of the heat energy released through burning the fuel raises the temperature of both the engine components and the oil. In this lesson, we will discuss the problems that can be caused by allowing the engine to become either too hot or too cool, and we will look at the systems that are fitted to an engine to maintain its temperature within safe limits. As we said, approximately 32% of the heat energy released through burning the fuel raises the temperature of both the engine components and the oil. If this temperature increase is not controlled, it can be the cause of several problems. The oil temperature will become too high, which will cause it to lose its lubricating properties, and as a consequence, the engine may suffer structural failure of some of the components. If the engine gets excessively hot, carbon deposits in the cylinder can become incandescent. The hot spots thus created can cause the mixture to ignite before the normal ignition point. This phenomenon is called pre-ignition. Excessively high temperatures can cause the combustion process to become unstable after the mixture has been ignited at the normal point. This is called detonation or knocking. Both pre-ignition and detonation result in a loss of engine power. They are fully explained in the lessons on fuel. Problems can also occur if the engine operates at too low a temperature. In order to obtain high values of thermal efficiency, we operate the engine at high temperatures. There are two reasons for this. Firstly, low engine temperatures increase the internal friction of lubricants by increasing the viscosity of the oil. This would increase the friction horsepower within the engine and thus reduce the brake horsepower available at the propeller. Secondly, the ability of the liquid fuel to change its state from liquid to vapour is reduced in a cold engine. This affects both the fuel mixture strength from cylinder to cylinder and the ability of the fuel to burn efficiently. In order to operate efficiently then, an engine must operate at the highest temperature consistent with safe operation. Variations in the ambient and engine internal temperatures mean that an engine needs a cooling system to maintain its temperature at the optimum level. The two types of cooling system used in aircraft piston engines are liquid cooling and air cooling. We will now look at these two system types, beginning with the liquid cooling system. The liquid cooling system shown in this diagram dissipates the heat generated in the engine by pumping a liquid through passages built into the cylinders and cylinder heads. This liquid is usually a mixture of water and glycol. The glycol acts as an antifreeze agent. The mixture of water and antifreeze is then passed through a radiator, which is mounted in the slipstream of the propeller. This placement ensures that, even with the aircraft stationary on the ground, there is a flow of cooling air across the radiator. The liquid cooling system is made up of a number of components. An engine-driven pump circulates the liquid through the engine. A thermostat controls the coolant temperature. The thermostat is a temperature-sensitive valve. It is designed in such a way that as the temperature of the liquid increases, it allows more liquid to pass through the radiator, increasing the cooling effect, and, as the liquid temperature falls, the thermostat reduces the flow, thus reducing the cooling effect. A header tank acts as a reservoir for the coolant liquid. Pipes allow the fluid to flow around the system. Air flowing across the radiator dissipates the heat from the coolant to the air. Because of the operation of the thermostat, the temperature of a liquid-cooled engine is maintained almost constant throughout the engine's operating range and with changes in environmental conditions. Modern aero-diesel engines tend to be liquid-cooled or utilize a combined liquid-air cooling system. Air-cooled engines use the airflow from the propeller slipstream and from the forward speed of the aircraft to transfer the heat generated in the engine directly to the air. The engine is surrounded by cowlings, which reduce drag and control the flow of air around the engine. The controlled flow ensures that all parts of the engine are equally cooled, and it thus prevents overcooling of the front of the engine. The two main factors governing the efficiency of an air-cooled system are 1. The ambient air temperature, which can vary widely with changes in climatic conditions and altitude. Dissipation of the heat generated in the engine will be more rapid as the air temperature decreases. And 2. The speed of the airflow passing over the cylinders, which is governed by the slipstream and thus will vary with the speed of the aircraft. Some engine installations require that care be taken when ground running to prevent overheating, because, as the aircraft is stationary, the only airflow over the engine comes from the propeller slipstream. On the type of installation where this is a problem, a fan may be fitted behind the propeller to obtain a greater airflow over the engine, as is shown in this diagram. The external surfaces of the air-cooled cylinder and the cylinder head are increased by the use of deep fins. The engine designer walks a fine line between ensuring that the pitch of the fins is such that a large fin area can be obtained, whilst ensuring that the fins are not too close, that the resistance to the airflow builds up pressure, which would tend to decrease the airflow and thus increase the drag. An average pitch for fins is 2 per centimetre. The fins have a thin cross-section. They may be extended at local hotspots so that their surface area increases in an attempt to produce an even temperature throughout the component, for example around the exhaust ports on the cylinder head. Baffles, which are shown here on this diagram, are air guides which direct the airflow completely around the cylinder. They must be close-fitting and provide a seal with the inside of the cowlings so that all the cooling airflow is directed around the cylinders. Care is taken to ensure that an even cross-sectional area is maintained so that the airflow does not slow down and cause drag. Cowlings must be close-fitting without dents or projections which may disturb the airflow over them. Any disturbance to the designed airflow will not only increase the drag, but also decrease the cooling effect it delivers. Cowl flaps may be fitted to enable control of the airflow through the engine. These flaps can be moved to any position from fully open to fully closed. The flaps may form a complete circle around the cowling. These types of cowl flaps are often known as gills. With the cowl flaps or gills open, the air flowing over the engine cowling causes a pressure drop at the cooling air outlet, thus accelerating the heated airflow and enabling it to maintain a high speed over the cylinders. As the air flows over the cylinders, it absorbs heat and expands. This increases its speed even more. Any increase in the speed of the air mass flow through the engine creates a reactive force, which, by acting forwards, tends to negate some of the total engine drag. The heat from the engine is not always transferred straight to the atmosphere. It can be used for heating the cabin of the aircraft, and directed when selected to supply hot air to remove ice from the carburetor. Both these uses are fully explained in other lessons. Where possible, engine components are made of materials with high heat conductivity. Most air-cooled engines have cylinder heads which are machined from forged aluminium alloy or steel, with, to obtain the best possible heat flow, a heavy deposit of copper on the combustion chamber face. The cooling system of the air-cooled engine has few moving parts, and thus the simplicity of the system makes it virtually maintenance-free. Whilst the liquid-cooled system requires regular maintenance and there is the risk of fluid leaks. These are the main reasons why an air-type cooling system is often preferred to liquid cooling on gasoline-powered aircraft piston engines. Nevertheless, it should be appreciated that a liquid cooling system is more efficient than an air cooling system. Liquid cooling gives better control of engine temperature, allowing tighter tolerances in the construction of the moving parts. It is for these reasons that liquid cooling systems are often used on very powerful petrol engines. Also, because of the higher temperatures involved, diesel engines are normally liquid cooled. The cylinder head temperature gauge is an engine instrument designed to aid the pilot in protecting the engine against excessive heat. The operation of the cylinder head temperature gauge is dependent on a sensor which is mounted on the engine cylinder head. The sensor is a thermocouple. The principle of operation of the thermocouple is covered in depth in the electrical and instrument objectives. What you need to understand here is that the sensor produces a very small voltage which is directly proportional to the temperature of the cylinder head. This voltage is sent to the gauge in the cockpit. The gauge in the cockpit is a millivoltmeter which has been calibrated in either degrees Celsius or Fahrenheit. If only one sensor is fitted, it will sample the cylinder head temperature of the hottest cylinder. The hottest cylinder is determined by extensive flight tests carried out by the engine manufacturers. It is usually one of the rearmost cylinders. That is the end of the lesson. Here is a summary of the main points. Overheating of the engine will cause the oil to lose its lubricating properties, leading to possible structural failure of some components. It can also cause both pre-ignition and detonation to occur. Overcooling of the engine increases the viscosity of the oil, leading to an increase in friction horsepower and a subsequent reduction in the brake horsepower available at the propeller. And the ability of the fuel to change its state from a liquid to a vapour is reduced. On an air-cooled engine, fins are used to increase the cooling area. Baffles direct the airflow completely around the cylinders. And cowl flaps or gills may be fitted to enable control of the airflow through the engine. The main advantage of an air cooling system is that its simplicity makes it virtually maintenance-free, whilst a liquid cooling system requires regular maintenance but gives much better control of engine temperatures. The cylinder head temperature gauge is an engine instrument designed to aid the pilot in protecting the engine against excessive heat. In this lesson, we will discuss how aircraft engines with and without cowl flaps should be operated in order to keep the engine temperature within safe limits. The cooling system for any particular type of engine is designed to ensure satisfactory cooling during cruising flight when the forward speed of the aircraft should give an adequate flow of cool air. It is a fact, however, that aircraft go through many different stages of flight other than just the cruise, when the airflow pattern will differ from the cruise standard. During a climb, when high power is being used, high temperatures are generated within the engine. Forward speed is, however, reduced, and thus airflow to the engine is also reduced. In this type of situation, the pilot should be aware of the possibility of overheating. Climbing at the best rate of climb speed for your type of aircraft is preferable to prolonged use of the best angle of climb speed, where the speed will be slower. Descending can also cause problems. Engine power is reduced and thus less heat is generated. If the aircraft is put into a dive, the increased speed will increase the flow of air over the engine and increase the possibility of overcooling it. The sudden change in temperature thus caused is known as thermal shock. This can cause components to fracture, particularly the engine cylinders. Improved control of engine temperature, which would minimize the occurrence of thermal shock, is possible where cowl flaps or gills are fitted, but these items may not be available on many light aircraft. On these aircraft, the pilot can control the engine temperature by either manipulating the airspeed, the engine power, or the mixture control. Cylinder head temperature is affected by mixture strength. This is fully covered in the lesson on mixture. The highest cylinder head temperatures are when a lean mixture is selected for economy or endurance cruise. It is easier for the pilot of an aircraft with variable cowl flaps to maintain control of the temperature of his engine by adjusting the opening of the flaps to suit the operating conditions. At high power settings and low airspeed, such as those experienced at takeoff and during a climb, the cowl flaps should be selected open to increase flow rate of air and so increase cooling. When selected to this position at takeoff, the protruding cowl flaps may increase drag. In the cruise at altitude, because the drop in air temperature at height will improve the efficiency of the cooling system, the cowl flaps may be partially closed to maintain the engine temperature. In descent, the cowl flaps should be closed in order to reduce the cooling effect of the airflow. The cowl flaps should be fully open for landing in preparation for a go-around should one become necessary. The length of time that high power settings are used on the ground should normally be limited, as the only cooling effect available is the propeller slipstream. This may not always be sufficient and overheating can occur, especially on hot and high airfields. Both cylinder head temperature and oil temperature should be closely monitored during ground running. The engine oil temperature is important because of the fact that engine components, such as the pistons and bearings, are cooled by the lubricating system. Prior to shutdown, the engine should be run at idle power for a short period until engine temperatures have reduced and stabilized. Shutting down whilst the engine is very hot can result in uneven cooling and possible damage through distortion of the components. That is the end of the lesson. A summary of the engine operating procedures for engines with and without cowl flaps is being displayed on the screen. Make sure you are familiar with it before leaving the lesson.
In this lesson, we will examine the properties of the fuel used in aircraft piston engines. Aircraft piston engines use gasoline, and gas turbine engines kerosene. Both of these fuels are produced from crude oil. In simple terms, the required oil is extracted from the crude oil by a distillation process. The oil is boiled in a furnace, and then the oil vapour is cooled in a distillation column. The various hydrocarbons in the oil all have different boiling points, so they condense out of the vapour and are tapped off at different points in the column. The heavy oils condense out first and are collected near the bottom. The process then continues up through the tower, with kerosene and gasoline, which are relatively light and volatile, being taken out near the top. Piston-engined aircraft use gasoline fuels grouped under the title aviation gasoline or avgas. Gas turbine engines use kerosene. Aviation gasoline is manufactured to conform with exacting specifications that are issued in the United Kingdom by the UK Aviation Fuels Committee on behalf of the Defence Material Standardisation Committee. The specification number for gasoline is Defence Standard or DEFSTAN 91-90. Aviation gasoline is graded by octane rating or performance number. The octane rating or performance number of a fuel is a measure of the fuel's resistance to detonation when subjected to high temperature and pressure. Detonation and octane ratings are fully explained in later lessons. The grades of aviation gasoline currently authorised and available are Avgas 100 and Avgas 100LL. In order to differentiate between grades, dyes are added to the fuels in accordance with an internationally agreed colour code to impart a distinctive colour. Avgas 100 is coloured green, has an octane rating or performance number of 100-130 and has a high lead content. Avgas 100LL has the same performance number as Avgas 100, but it has a lower lead content. It is coloured blue. Avgas has a specific gravity of 0.72 at 15 degrees Celsius. Specific gravity is important, as fuel is delivered by volume, but pilots need to know its mass or weight, as the energy available from the fuel is dependent on its mass, not its volume. And of course the mass of the fuel affects the aircraft's all-up mass. Equipment used to dispense avgas is coloured red to prevent cross-contamination with other fuels. MoGas or motor gasoline can sometimes be used in certain airframe engine combinations, but only under the conditions specified in Civil Aviation Authority airworthiness notices numbers 98, 98A, 98B and 98C. Because of the higher volatility and water content of MoGas, carburetor icing and vapour locking are much more likely to occur if this fuel is used. The subject of carburetor icing is fully covered in another lesson. Information and advice on the use of MoGas can be found in CAA Safety Sense Leaflet number 4. Some diesel aero engines are designed to run on diesel fuel. However, most diesel aero engines use AVTUR. This is the kerosene-type fuel used by gas turbine engines, and is fully described in the gas turbine engine fuel lesson. Aviation turbine gasoline, or AVTUR, is widely available. It is less volatile and less of a fire hazard than avgas. Although the calorific value of AVTUR is slightly lower than that of avgas, AVTUR is more dense, so it contains more energy per unit volume, thus giving better range and endurance. On the negative side, AVTUR begins to become more viscous at low temperatures, therefore requiring some kind of fuel heating system to be built into the supply line. We've already stated that aviation fuels are given specifications by the UK Aviation Fuels Committee on behalf of the Defence Material Standardisation Committee. We will now look at some of the characteristics that have to be assessed before such a specification can be fulfilled, beginning with the calorific value of the fuel. The calorific value of a fuel is a measure of the amount of heat energy that will be released during its combustion, and is measured in British thermal units per pound or kilojoules per kilogram. The calorific value of a fuel varies with its chemical composition. Fuels with a high hydrogen content having a higher calorific value per unit weight. The calorific value of a fuel is also related to its specific gravity. The higher a fuel's specific gravity, the greater will be its mass, and hence its calorific value per unit volume. A volatile liquid is one which is capable of changing readily from the liquid to the vapour state by the application of heat, or by contact with a gas into which it can evaporate. As you will see in a later lesson, fuel is added to the air in the carburettor. The volatility of gasoline determines the efficiency with which the fuel and air mix. However, the time in which this mixing takes place is so short that some of the fuel remains in the form of minute droplets, the evaporation of which occurs in the induction system. The more volatile the fuel is, the better will be this mixing and evaporation. A liquid boils when its vapour pressure is greater than the atmospheric pressure acting on the surface of the liquid. This means that as the atmospheric pressure reduces with increases of altitude as the aircraft climbs, the fuel vaporizes at a lower temperature. This is generally referred to as low-pressure boiling. If the fuel is very volatile, not only will there be excessive losses through evaporation in the aircraft's fuel tanks, but the fuel will tend to boil and vaporize at the depression or inlet side of the fuel pump, causing bubbles and vapour locks to form, which can interrupt the flow of fuel to the carburettor. The tendency for carburettor icing to form under certain atmospheric conditions is also increased with the use of volatile fuels. As we said previously, carburettor icing is covered fully in another lesson. A number of the hydrocarbon compounds which are present in gasoline have a considerable attraction for the oxygen in the air. When they come into contact with air, they oxidize and undergo chemical changes to form heavy resinous gummy compounds and corrosive bodies. It is essential that these potentially unstable hydrocarbons are not allowed to oxidize. This is prevented by the addition of oxidation inhibitors to the fuel at the refinery. Sulfur and sulfur compounds, when burnt in air, form sulfur dioxide. This combines with the moisture content of the exhaust products to form a sulfurous acid, which is extremely corrosive to the exhaust system. It is important that the sulfur content is kept as small as possible. In aviation gasoline, the maximum amount of sulfur permitted is 0.001%. That is the end of the lesson. Being displayed on the screen is a table listing the properties of the two grades of avgas that are authorized and available. And here is a list of the advantages and disadvantages of avtur, which may be used in aerodiesel engines.
In this lesson, we will look at the combustion process in a piston engine, and then we will go on to examine the problems of detonation and pre-ignition, both of which can occur during the combustion phase. Combustion of the air and gasoline mixture in a piston engine is the controlled rate of burning. It is not an explosion. The mixture induced into the cylinders consists of gasoline vapour, 84.2% carbon and 15.8% hydrogen by weight, and air, 78% nitrogen, 21% oxygen and 1% other inert gases. When combustion has been completed, the hydrogen in the fuel will have combined with the oxygen in the air to produce H2O in the form of water vapour. And the carbon in the fuel will combine with the oxygen in the air to form carbon dioxide, or CO2. The nitrogen and other gases play no active part in the combustion process, but they do form the bulk of the gas that is heated and expanded to create pressure energy. The nitrogen also slows down the rate of combustion. Without nitrogen, combustion would be an explosion with far too rapid a temperature and pressure rise to allow it to be harnessed to do useful work. When normal combustion takes place, the compressed mixture in the cylinder is ignited by the spark and burns steadily with a flame front velocity or flame rate of 60 to 80 feet per second, giving a steady and smooth temperature and pressure rise in the combustion chamber. Maximum pressure will be generated when combustion has been completed, and ideally this should occur when the crank is at 8 to 10 degrees after top dead centre, TDC, where, because of the ineffective crank angle, the volume of the combustion chamber is still at a minimum. Should maximum pressure conditions arise in advance of this, that is at or before crankshaft reaches top dead centre, the engine would tend to run backwards. As combustion takes a period of time, albeit a short one, in order for combustion to be completed when the piston is 8 to 10 degrees after top dead centre, the spark must occur before the piston reaches top dead centre. The flame rate remains reasonably constant, so if the ignition point remains the same, the point in the cycle where combustion is completed will vary with variations in engine speed. At low engine speeds, it is necessary to initiate ignition later in the cycle to prevent the maximum pressure building up before the piston reaches top dead centre. The term used for this is retarding the ignition timing. As the engine speed increases, it is necessary to initiate ignition earlier in the cycle so that the maximum pressure still occurs at 8 to 10 degrees after top dead centre. This is known as advancing the ignition timing. The flame rate can vary slightly. The mixture will burn faster if it's made richer, that is to say, the proportion of fuel in the mixture is increased. This is because the proportion of nitrogen will be reduced. The mixture will also burn faster if the pressure in the cylinders increases. An instance of both these events occurs on takeoff, when it's necessary to richen the mixture strength in order to ensure stable combustion because the engine is producing high power. This at least partly offsets the requirement to advance the ignition timing at high engine speed. Because single-engine light aircraft have a greater need for reliability than for efficiency, the ignition timing is usually fixed at an intermediate position and not adjusted. As we have said, during normal combustion, the flame travels smoothly and steadily through the mixture as the advancing flame front heats the gases immediately ahead of it, so that they in turn burn. Detonation, if it occurs, happens after ignition and is unstable combustion. Detonation happens because progressively more and more heat is concentrated in the flame front, which is brought to bear on the remaining unburnt portion of the mixture, termed end gas, and its temperature is raised. In addition, the burnt gases have expanded, so the end gas is subjected to an increasing pressure and therefore its temperature increases further. If there is sufficient pressure and heat available to bring all the end gas to the point of combustion at the same instant, it will explode or detonate. The flame rate will increase to 1,000 feet per second, with a degree of violence which will depend on the amount of end gas that remains. The explosion of the end gas can cause the piston crown to burn and eventually to collapse. This picture shows a piston which has been severely damaged by detonation. The piston crown has been burnt and eventually it has disintegrated. Overheating of the combustion chamber can also occur. This may cause the valves to split and distort. It might also damage the spark plug electrodes. The damage shown here is consistent with being caused by detonation. There is also a sudden rise in pressure as detonation occurs, which applies a shock loading to the engine component parts which may cause mechanical damage, particularly to the big end bearings, and even the connecting rod, although the case shown here is extreme. Finally, because the maximum pressure is generated before the piston is in the correct position to utilize it, the piston has to overcome a high back pressure and power is lost. There are a number of reasons why the temperature in the combustion chamber can become excessive, causing detonation to occur. Any of the following, either individually or in combination, can give rise to the onset of detonation. Any condition that heats the charge before combustion will increase the temperature of the end gas. Preheating the air before it enters the engine by the use of carburetor heat to overcome carburetor icing, for instance, or overcompression in the supercharger or turbocharger may well give rise to excessive charge temperatures. The weaker the mixture selected, the hotter will be the temperature of combustion. Conversely, if the mixture is made richer, it will burn cooler and more quickly, thus combating detonation. The formation of carbon, or coke as it is sometimes known, in the cylinder head will prevent heat dissipation, possibly bringing the temperature of combustion up to the point of detonation. Advancing the ignition timing, in other words igniting the mixture too early, may cause cylinder pressures and temperatures to rise too rapidly, possibly causing detonation to occur. If a fuel with an octane rating lower than that which is recommended is used, it will promote detonation, especially under high power conditions. It's important, therefore, that fuel of the recommended octane rating is used. If this fuel is not available, then one with a higher octane rating may be used. The fact that detonation is occurring can be recognized by a metallic knocking sound, sometimes called pinging, which is caused by the violent vibrating pressure waves striking the walls of the combustion chamber. A great deal of damage may be done under high power conditions, particularly in an aircraft where, because of the noise created by the propeller, the detonation may go unnoticed until it is too late. Engine designers can help to prevent detonation by ensuring that the flame is started from the vicinity of some hot spot, such as the exhaust valve, so that the end gas is pushed away from the hotter parts of the combustion chamber and compressed into a cooler part. In order to reduce the time taken for the flame front to travel across the combustion chamber and therefore the risk of detonation, some engines are designed with two spark plugs which initiate the flame simultaneously from two different points in the chamber. The pilot can also take a number of actions to help prevent detonation. On aircraft with variable pitch propellers, the same power may be obtained at a higher engine speed by using a finer propeller pitch. This enables a smaller throttle opening to be used, which helps in two ways. The smaller throttle opening reduces the cylinder pressure, and the higher running speed cuts down the time available for detonation to develop. Carburetor heat should not be used at very high engine power settings, such as during takeoff. A rich mixture should be used at high power settings. Pre-ignition is the ignition of the charge before the spark occurs at the sparking plug. This is usually caused by a local hotspot in the combustion chamber, such as incandescent carbon or very hot sparking plug points. Pre-ignition can cause the engine to run very erratically. If, as in a car, the ignition switch is used to shut down the engine, it may continue turning over if it is still supplied with fuel. This is called running on. The engine performance will suffer greatly because the ignition is effectively retarded. This in turn will cause the engine to overheat, which exacerbates the situation. Here are the main points you should take from the lesson. When normal combustion takes place, the compressed mixture in the cylinder is ignited by the spark and burns steadily with a flame front velocity, or flame rate, of 60 to 80 feet per second. In order for combustion to be completed when the piston is at 8 to 10 degrees after top dead centre, the spark must occur before the piston reaches top dead centre. The mixture will burn faster if it's made richer, or if the pressure in the cylinders increases. Pre-ignition is the ignition of the charge before the spark occurs at the sparking plug. This is usually caused by a local hotspot in the combustion chamber. When you are happy with these points, move on to see a summary of the causes of and the methods used to prevent detonation. Detonation occurs after ignition and is unstable combustion. Detonation can cause serious damage to the engine. Detonation can be caused by the use of hot air to combat carburetor icing, overcompression in the supercharger or turbocharger, a weak mixture, a buildup of carbon in the cylinder head, advancing the ignition timing, or using a fuel with a lower octane rating than that which is recommended. Detonation can be prevented by starting the flame from the vicinity of a hotspot such as the exhaust valve, using two spark plugs which initiate the flame simultaneously from two different points in the chamber, using a finer propeller pitch, avoiding the use of carburetor heat at very high engine power settings, and using a rich mixture at high power settings. In this lesson, we will discuss the meaning of the octane ratings which are used to grade aviation gasoline. We will also look at the advantages and disadvantages of adding lead to the fuel. We've already stated in a previous lesson that if a fuel of a lower octane rating than that recommended is used, it will promote detonation, especially under high power conditions. The octane rating of a fuel is, therefore, obviously very important. To determine the anti-detonation or anti-knock qualities of a fuel, its combustion characteristics can be compared with those of a mixture of two chemically pure fuels, called reference fuels, under laboratory conditions. Isooctane is one of the reference fuels. It has very good combustion characteristics and shows little tendency to detonate when mixed with air and ignited at high temperatures, so it's given a rating of 100. Normal heptane is the other reference fuel. It detonates very readily and is given a rating of 0. A special engine is first run using the fuel under test. The compression ratio is increased until the fuel begins to detonate. The engine is then run again, but this time with the compression ratio fixed at the detonation point of the fuel under test. Initially, the engine is run using only isooctane. Then normal heptane is added until detonation takes place. The fuel under test is given an octane rating equal to the percentage of isooctane in the equivalent reference fuel mixture. If, for instance, that blend of reference fuels was 95% isooctane and 5% normal heptane, the fuel under test would be given an octane rating of 95. The octane rating is therefore a measure of the fuel's anti-detonation capability. The higher the octane rating, the better is the fuel's anti-detonation capability. Fuels with better anti-detonation characteristics than isooctane are now available. The scale has been extended beyond 100 to allow for these fuels and is technically no longer an octane rating scale, but a performance number scale. However, you will still often find it referred to as an octane rating. Originally, tests were based on an air-fuel ratio which gave maximum detonation, but this condition is not truly representative of the working range of the engine. Maximum detonation occurs with the weak mixtures used for economy during cruise. but for takeoff and climbing, rich mixtures are used. It's important to know how the fuel will behave under these varying mixture strengths, and so aviation fuel has two ratings. The weak mixture rating is used in the fuel's name. Avgas 100LL has a performance number of 100/130. The lower figure of 100 indicates the weak mixture octane rating, and the higher figure of 130 the rich mixture octane rating. The onset of detonation can be delayed by putting very small quantities of additives into the fuel, the principal one being tetraethyl lead or TEL. The action of tetraethyl lead is to reduce the temperature of combustion and increase the flame rate, so it increases the octane rating of the fuel. Lead oxide is formed during combustion. It stays inside the engine and has a corrosive effect on the exhaust valve seat, and the sparking plug electrodes. In order to prevent the formation of lead oxide, ethylene dibromide is added to the fuel. This changes the reaction which occurs during combustion so that the lead oxide is converted to lead bromide. Lead bromide is volatile and is ejected with the exhaust gases. The lead content of the exhaust gas can be breathed in. Lead has an extremely harmful effect on the human body, and even a small amount can kill. For this reason, there is a great deal of pressure on the aviation industry to stop using leaded fuels. The use of high-octane fuel in the engine has several benefits. The use of a higher octane fuel will allow the use of an increased compression ratio. An increased compression ratio gives an increase in thermal efficiency, better fuel consumption, and an increase in engine power. Higher octane fuel used in an engine will allow the use of increased induction pressure, leading to greatly increased power from a given engine by the use of a supercharger. This is because the power output of an engine is directly proportional to the weight of mixture burned in a unit time. Increased induction pressure will increase this weight. The piston engine works by converting chemical energy into heat energy, which is then converted into mechanical energy. A considerable amount of energy is lost in the form of heat to the cylinder walls and the piston crowns. The exhaust gases also remove heat as their temperature is still high when they are expelled from the cylinder during the exhaust stroke. Additional work is done in overcoming the internal friction of the engine. The net result is that under the best conditions, rather less than 30% of the heat value of the fuel is converted into useful work at the propeller shaft. That is the end of the lesson. Here are the main points you should take from it. The higher the octane rating or performance number of a fuel, the better is its anti-detonation capability. Aviation fuel has two ratings. The lower figure indicates the weak mixture octane rating, and the higher figure the rich mixture octane rating. The onset of detonation can be delayed by adding very small quantities of tetraethyl lead or TEL to the fuel. The advantages of using high-octane fuel in the engine are an increased compression ratio capability leading to increased thermal efficiency, better fuel consumption, and an increase in engine power. An increased induction pressure can be used, which will produce a greatly increased power output.
Although air and gasoline vapour will burn when mixed in proportions ranging between 8:1, which is considered to be rich, and 30:1, which is used in some lean burn automobile engines, complete combustion only occurs with an air-gasoline ratio of 14.7:1 by weight. This ratio is termed the stoichiometric or chemically correct ratio, At this ratio, all of the oxygen in the charge combines with all of the hydrogen and carbon during combustion. For the purposes of this lesson, we'll restrict our numerical definition of the chemically correct ratio to two significant figures. Thus, we'll specify 15:1 as the chemically correct ratio for air and gasoline. It's important to remember that the chemically correct mixture does not give the best results in a piston engine, because the temperature of combustion is so high at this ratio that power can be lost through detonation. In practice, particularly in a carburetor induction system, mixing of the air and fuel particles and their distribution is less than perfect. This results in some parts of the induction system having a richer mixture and others having a weaker mixture than the optimum strength. This variation in mixture strength may even exist between one cylinder and another adjacent to it, as is evident in this example of a simple automotive twin carburetor induction system, where the difference in the distance that the air-fuel stream has to travel between the carburetor and, say, the number 1 and number 2 cylinders will have a quantifiable effect on performance. Having a slightly rich mixture does not have much effect on power, since all of the oxygen is still consumed and the excess of fuel merely serves to slightly reduce the effective volumetric efficiency of the engine. In fact, the cooling effect of the evaporating fuel can to some extent be beneficial in cooling the charge temperature below the level where it might otherwise detonate. Running the engine on a weak mixture, however, rapidly reduces power, since some of the inspired oxygen is not being utilized. The power reduction thus suffered is much greater than that which results from a slight richness of mixture. It is, therefore, quite common to run aircraft engines which are fitted with carburetors, when maximum power rather than best fuel economy is the objective, at somewhat richer than the chemically correct mixture, for example about 12.5:1, to ensure that no cylinder is left running at severely reduced power from being unduly weak. A mixture which is weaker than the chemically correct ratio, besides burning at a lower temperature than that which would occur with the chemically correct ratio, also burns at a slower rate than the chemically correct ratio, because of the greater proportion of nitrogen in the cylinder. Power output thus decreases as the mixture is weakened, but because of the increase in efficiency which results from cooler burning, and the associated decreased occurrence of detonation, the fall in power is proportionally less than the decrease in fuel consumption. Thus, the specific fuel consumption decreases as the mixture strength is weakened below 15:1. For economical cruising at moderate power, air-fuel ratios of 18:1 may be used, an advance in the ignition timing being necessary to allow for the slower rate of combustion. The current number of modern aircraft with the facility to vary the ignition timing in flight is limited. However, following the recent introduction of electronic engine control, a rise in this number is likely. With extremely weak mixtures, the gases may still be burning when the exhaust valve opens, exposing the valve to high temperatures, which may cause the valve to crack or distort. As the inlet valve opens, the heat of the exhaust gases remaining in the cylinder may still be so high that it could ignite the mixture in the induction system, and popping back occurs through the induction manifold. This slow burning also causes overheating, because a certain amount of the heat generated in combustion is not converted into work by expanding the gases in the cylinder as it should be. It therefore remains in the cylinder and has to be dissipated by the cooling system. The mixture requirement is ultimately dependent upon engine speed and power output. This diagram shows typical air-fuel mixture curves. Note that a rich mixture is required for starting and slow running. There are two reasons for this. The first reason concerns the fact that fuel will only burn when it's vaporized and is mixed with air. When first starting, the engine will be cold, and there is little heat to assist the vaporizing process. Therefore, only the lightest fractions of the fuel will vaporize. To make sure that there is sufficient fuel vapor in the cylinders to support combustion, a rich mixture is therefore required. The second reason concerns the valve timing. As we've already learnt, the exhaust valve timing is given a certain amount of lag, so that full advantage can be taken of the considerable inertia of the gases at normal engine speeds to obtain efficient scavenging of the burnt gases, and to give impetus to the incoming charge. However, as engine speed reduces, the gas velocity falls, and more of the burnt gases remain in the cylinder, whilst at still lower speeds, such as idling speed, there is the tendency for exhaust gases to be sucked back into the cylinder by the descending piston before the exhaust valve closes. The consequent dilution of the induction gases is such that, to maintain smooth running, a rich mixture is required. The cruise portion of the diagram shows that this is really the only time during which the pilot has any choice in what mixture to set. If time is no object, then during cruising flight, only moderate power is required from the engine. Thus, an economy cruise setting of approximately 17.4 to 1 can be used. Fuel consumption will decrease accordingly. On the other hand, if speed is of the essence, then a mixture setting which gives performance cruise power can be selected, say somewhere in the region of 14.4 to 1. The fuel consumption will of course rise, in some cases by as much as 20%. When higher power is required, for instance when climbing, the mixture is enriched to about 11 to 1. The extra fuel, in vaporizing, cools the mixture and reduces the tendency to detonate. When full power is selected for takeoff, the mixture must be enriched to about 10 to 1. Apart from the cooling effect, the excess fuel is wasted, for there is insufficient oxygen available for it to burn completely. The higher power results from a greater weight of charge induced in a given time, and not because of mixture enrichment. In practice, excess fuel vapour is not scavenged as vapour, because the oxygen is shared out to some extent, so that carbon monoxide is produced during combustion as well as carbon dioxide. With very rich mixtures, some of the carbon fails to combine with oxygen at all, and is exhausted as black smoke. Because the density of the air decreases with increase of altitude, as the aircraft altitude increases, the weight of air drawn into the cylinder decreases. For a given intake velocity, the pressure drop in the carburettor venturi will decrease as ambient density decreases. However, the fuel flow due to this pressure drop will not decrease by the same proportion, and so the mixture will become richer. If we are to operate the engine efficiently when flying at altitude, then it becomes imperative that we have some method of defining and regulating the mixture strength. We'll look at two methods which can be used to maintain the correct mixture control. The first method that we'll examine presumes some knowledge of the effects that mixture change will have on the engine. Bear in mind that as the mixture control is moved from fully rich to a weaker setting, the air-fuel ratio approaches the chemically correct value of approximately 15 to 1. At this ratio, all of the air and the fuel are consumed, and the heat released by combustion is at its maximum. More heat means more power. With a fixed-pitch propeller, the RPM will rise, and airspeed will increase as more power is produced. If the mixture is weakened even more, the RPM will drop. Pushing the mixture control back to where the chemically correct mixture was found will bring the engine speed back up, but this cannot be maintained without risking the generation of detonation. To prevent this happening, the mixture control should be moved to a slightly richer position, when the RPM will fall slightly. The second method utilizes the exhaust gas temperature gauge. The exhaust gas temperature system is powered by a thermocouple, which is fitted into the exhaust pipe of the hottest cylinder on the engine. The thermocouple produces a voltage which is directly proportional to its temperature. The voltage is indicated on a gauge which is calibrated to show exhaust gas temperature. If the mixture control is moved towards lean, the temperature will peak at the ratio of 15 to 1. It should be remembered that this ratio should not be used, as detonation can occur. The mixture control should then be moved from the peak exhaust gas temperature position towards rich, and the exhaust gas temperature will drop. The aircraft's flight manual will specify a temperature drop which will give the rich cruise setting. This concludes the lesson on mixture.
Piston engines, particularly those which are fitted with float chamber carburetors, can be affected under some environmental conditions by the problem of engine induction system icing. There are three forms of engine induction system icing. They are carburetor icing, fuel icing, and intake or impact icing. In this lesson, we will examine the three types of icing. We will look at how the pilot can recognise the onset of induction system icing and at how the build-up of ice can be prevented. We will begin by looking at carburetor icing. The most common type of induction system icing is carburetor icing, sometimes known as refrigeration icing. Carburetor icing forms mainly in float-type carburetors. You will recall from the introductory lesson that in a convergent-divergent duct or venturi there is a reduction in the pressure of the air passing through it. This is accompanied by a drop in temperature. For this reason, the temperature of the air passing through the carburetor venturi falls. The temperature of the air is further reduced by the vaporizing fuel removing heat from it. The temperature reduction may be as much as 20 to 30 degrees Celsius and results in moisture in the induction air forming ice. The ice gradually builds up, constricting the venturi and upsetting the fuel-air ratio. It causes a progressive decrease in engine power. The ice may prevent operation of the throttle butterfly valve. And if action is not taken, it may accumulate sufficiently to block the intake completely and stop the engine. Reduced power settings are more conducive to icing in the throttle area because there is a greater temperature drop at the carburetor venturi and the partially closed butterfly can more easily be restricted by the ice buildup. Carburetor icing is not confined to cold weather and will occur in warm weather if the humidity is high enough. This chart shows the range of temperatures and the different power settings within which carburetor icing can affect the engine. The diagram has outside air temperature along the bottom and dew point up the side. The diagonal lines show the level of humidity in the air as a percentage. When the temperature and dew point are equal, the relative humidity will be 100% and cloud or fog will form. You can see from the diagram that when conditions of medium to high humidity occur in temperatures ranging from as low as -7 degrees Celsius to as high as +33 degrees Celsius, carburetor icing may occur at almost all power settings. This temperature and humidity range occurs throughout the year in all areas of the United Kingdom and Europe, and therefore pilots should be constantly aware of the possibilities of carburetor icing. At temperatures of -10 Celsius or below, any moisture in the air will be already frozen and will pass through the carburetor without sticking. Impact or intake ice forms from water which is present in the atmosphere in the form of snow, sleet or supercooled water droplets. The ambient temperature at which impact ice may be expected to build up most rapidly is about -4 degrees Celsius in conditions in which visible ice is forming on other parts of the aircraft. Because of the inertia of the water which causes it, impact ice forms on surfaces which obstruct or change the direction of the induction airflow. It builds up on the air intakes, filters and bends in the intake duct. Fuel ice is produced by moisture in the fuel coming out of suspension and being frozen by the low temperatures in the venturi of the carburetor. This ice tends to stick to the inlet manifold around its corners and will reduce air and fuel flow into the engine. The indications to the pilot of any form of induction system icing on an aircraft with a fixed pitch propeller would be a gradual drop in engine RPM, which may be accompanied by engine rough running and vibration. In an aircraft which is fitted with a constant speed propeller, ice formation would be indicated to the pilot by a drop in manifold pressure or a reduction of airspeed in level flight. Induction system icing is prevented or cleared by heating the intake air in an exhaust gas heat exchanger before it reaches the carburetor. The system is known as carburetor or carb heat. The air supply is usually controlled by use of a manually operated carburetor heat control, marked hot and cold or on and off. In the hot or on position, a valve is repositioned to bypass the normal intake filter and feed the induction air from the heated source. It is worth noting that the hot air supply is not filtered. Carburetor heat does not provide instant relief when it is applied after ice has formed in the system. When induction system icing is suspected, the carburetor heat control should be selected on or hot and left in this position for a sufficient length of time to clear the ice. Any ice that has formed passes through the engine as water. Engine roughness and further power loss may occur as the water passes into the cylinders, and pilots should not be tempted to return the heat control to off or cold, thinking that the situation has become worse since they applied carburetor heat. It can take up to 1 minute or even longer depending on the severity of the icing for the ice to clear and the engine to run normally. Partial heat should not be used unless the aircraft is equipped with a carburetor air temperature or CAT gauge. When using carburetor heat, there are a number of factors which must be understood about its effects. The application of hot air into the induction system caused by the selection of carburetor heat reduces the density of the air and thus its mass. This causes a reduction in power output in the region of 15%. It also creates a richer mixture which may cause rough running. Heat should not be applied at power settings greater than 80% as there is a danger it will cause detonation and, as a consequence, engine damage. Detonation is fully explained in another lesson. Having said that, induction system icing should not normally occur at power settings which require a wide throttle valve opening. The continuous use of carburetor heat should be avoided because of both the change of mixture strength and also the increase of engine temperature it causes. Heat should be used only for a sufficient period of time to restore engine power to its original level. This restoration of power when the control is returned to off will be indicated to the pilot by the engine RPM or the manifold pressure increasing to above its level prior to the application of heat. The construction and operation of engines fitted with fuel injection systems are covered in another lesson. As far as icing is concerned, the main differences between this type of engine and one with a carburetor are that a fuel injection engine does not have a carburetor venturi, so there is no problem with carburetor icing. And because the fuel is injected at the cylinder head, where there is sufficient heat for fuel vaporization, there is no problem with freezing of any moisture released. However, impact icing can be a problem and must be protected against. These engines usually have an alternate air system, where a supply of warm air from inside the cowlings can be selected if icing is suspected. Because they have no carburetor and therefore no venturi reducing the air temperature, diesel engines do not suffer from carburetor icing. The fuel is injected directly into the cylinder, so there is no problem with fuel icing. Impact icing at the air inlet filter is overcome by the use of ice guards, which bypass the filter when it becomes blocked with ice. The problem of fuel solidification, known as waxing, where the fuel viscosity increases due to low temperatures, is overcome by putting additives in the fuel, or by using heaters in the fuel lines or filters to preheat the fuel. That is the end of the lesson. Here is a summary of the main points that you need to take from it. The three forms of induction system icing are carburetor icing, fuel icing, and intake or impact icing. Ice in the induction system may accumulate sufficiently to block the intake completely and stop the engine. Carburetor icing may occur when conditions of medium to high humidity occur in temperatures ranging from -7 degrees Celsius to +33 degrees Celsius. Induction system icing is prevented or cleared by heating the intake air in an exhaust gas heat exchanger before it reaches the carburetor. The indication of induction system icing on an aircraft with a fixed pitch propeller is a gradual drop in engine RPM, which may be accompanied by engine rough running and vibration. In an aircraft which is fitted with a constant speed propeller, ice formation is indicated by a drop in manifold pressure or a reduction of airspeed in level flight. When carburetor heat is selected with no ice present, the engine RPM will fall, then rise back to its previous reading when the heat is selected off. When carburetor heat is selected on with ice present, the engine RPM may rise. Then when the heat is selected off, the RPM will rise to a higher level than it was at before the heat was applied. To protect fuel injection systems from the effects of impact icing, an alternate air system, using a supply of warm air from inside the cowlings, can be selected if icing is suspected. In this lesson, we will look at the operational procedures governing the use of carburetor heat both on the ground and in flight. Use of the carburetor heat control on the ground should be kept to a minimum because the air then fed into the engine is not filtered and thus may feed dust and dirt into the system. This will cause heavy additional wear on the pistons and cylinder walls. However, induction system icing can occur during taxiing at small throttle settings or when the engine is at idle RPM. In these circumstances, the pilot must ensure that carburetor heat is used before takeoff to clear any ice. The pilot must, however, ensure that carburetor heat is selected to off before opening the throttle to full power and check that the correct takeoff RPM or manifold pressure is obtained. A functional check of the carburetor heat system should be made before takeoff. The indications obtained during the check, providing there is no ice present, are that the engine RPM will drop by approximately 100 RPM when carburetor heat is selected to on or hot. The engine RPM will only return to the selected setting when the carburetor heat is selected to the off or cold position. Do not use carburetor heat for takeoff during the climb. or any time at power settings above 80%. Throughout the flight, the pilot must be aware of conditions which are likely to cause induction system icing: damp, cloudy, foggy or hazy days, or times when flying either close to cloud or in rain or drizzle. You should also be alert for an unaccountable loss of engine RPM or manifold pressure. Frequent checks for induction system icing should be made by selecting carburetor heat on for a period of between 15 to 30 seconds, noting the engine RPM prior to system selection, then the subsequent drop of engine RPM as heat is applied. Should either the engine RPM increase when carburetor heat is applied, or the engine RPM return to a higher figure than was apparent when carburetor heat was last selected off, then ice is present in the induction system. Carburetor heat should be used continuously while flying in icing conditions. Icing is likely to occur during long periods of flight at reduced power, such as during a glide descent or a letdown to an approach and landing. This is because the heat required to melt the ice is derived basically from the engine, and during long descents the amount of heat available will diminish, thus reducing the effectiveness of the hot air system. Where icing conditions exist in the atmosphere, carburetor heat should be selected to on. Before reducing power, so that maximum benefit is gained from the hot engine before its temperature starts to reduce. To help maintain engine temperatures and provide sufficient heat to enable the system to melt any ice, it is necessary to increase power periodically to a cruising setting at intervals of between 500 and 1,000 feet during the descent. The carburetor heat selector should remain at off during the approach and landing, except for when making a glide approach. But if icing conditions are known or suspected, carburetor heat should be selected on. However, the carburetor heat control must be returned to off or cold before applying power during a roller landing or when carrying out an overshoot. During hot or dry weather conditions, selection of carburetor heat on may cause the mixture to become so rich that combustion may not continue, causing the engine to suffer what is known as a rich cut. Pilots should therefore consider the use of carburetor heat very carefully when flying in these conditions. That is the end of the lesson. A table summarizing the use of carburetor heat is being displayed on the screen. Study it carefully before leaving the lesson. In this lesson, we will look at the fuel injection systems which are used instead of carburetors on some aircraft piston engines. The injection system most usually employed is of the low-pressure continuous flow type. This system comes in two forms. Some fuel injection systems operate in a similar way to the carburetor by injecting fuel under pressure into the intake close to the throttle valve. However, the most commonly used system is the one highlighted here, where fuel is sprayed continuously into the induction port of each cylinder as close to the inlet valve as possible, and it is this type of system that we will study in this lesson. We will also look at the type of fuel injection systems in use on diesel engines. The advantages of a low-pressure, continuous flow type of indirect fuel injection system are low operating pressure, good fuel distribution, freedom from icing problems, and the ability to use a pump which does not have to be timed to the operating cycle. Because of the method of operation of the injector, no special idling arrangements are required. and a separate priming system for engine starting is usually unnecessary. The main components in the system are a fuel pump or pumps, a fuel control unit, a fuel manifold or distribution valve, a discharge nozzle for each cylinder, and a throttle valve to control airflow to the engine. A fuel pressure gauge is fitted to enable mixture adjustments to be managed. The system is normally equipped with 2 fuel pumps, which are arranged in parallel. One pump is driven by the engine, and the other is powered by an electric motor. Because of the parallel pump arrangement, fuel under positive pressure from the electrical pump can flow independently of the engine-driven pump. This allows the electrical pump to be used in case of a malfunction of the engine-driven pump and for engine priming and starting. The fuel control unit is mounted on the intake manifold and contains the air throttle assembly and 2 valves which control the fuel flow to the engine. These are the fuel metering valve or throttle metering valve and the mixture control valve. The air throttle assembly contains the air throttle valve, which is connected to the pilot's throttle lever and controls airflow to the engine. Note that in this type of system, no venturi is required to suck fuel into the airstream. Thus, the chances of encountering icing problems in the inlet manifold are much diminished. The fuel metering valve is mechanically connected to and moves with the throttle valve. It controls the flow of fuel into the engine according to the position of the throttle valve. Thus, fuel flow to the manifold valve and subsequently the injector nozzles is proportional to the airflow. The mixture control valve is connected to the pilot's mixture control lever. By moving the mixture control lever and thus repositioning the mixture control valve, the air-fuel ratio can be varied from the basic setting of the fuel metering valve as required by operating conditions. The mixture control valve can also be closed off completely, stopping the engine and acting as the idle cut-off control. The fuel manifold valve is located on the engine crankcase. It is the central point for distributing metered fuel to the engine. It contains a spring-loaded ball valve. When the engine is stopped, the ball valve is closed and no fuel can flow to the engine. As fuel pressure builds up as a result of engine rotation or booster pump operation, the ball valve opens, allowing fuel to flow to all of the discharge nozzles simultaneously. When the inlet fuel pressure drops below a certain level, for instance at engine shutdown, the spring will push the ball valve closed, shutting off all the fuel to the discharge nozzles. This stops both vapour locks occurring in the delivery line and the engine running on when idle cut-off is selected. A fuel discharge nozzle is located in each cylinder head, with its outlet directed towards the inlet port. Nozzles are calibrated in several ranges and are fitted to individual engines as a set, each nozzle in a set having the same calibration. Normally aspirated engines use a nozzle equipped with a fixed calibrated orifice, which has a series of holes drilled just below the orifice chamber for air entry to a lower chamber. A stainless steel shroud covers this part of the nozzle. As fuel passes through the calibrated orifice to the lower chamber, ambient air is pulled under the shroud and through the screen, finally mixing with the fuel as it is sprayed into the intake port. The fuel injection units used on the engines used in most light aircraft do not need heated air for the purpose of induction venturi icing protection. However, in order to prevent manifold air starvation caused by the filter being blocked with ice, an alternate air system is usually fitted. When a pilot first encounters flight conditions where the inlet filter may become blocked by ice, he should actuate the alternate air door. This will shut off the ram air inlet and, at the same time, admit unfiltered air from inside the cowlings. In a diesel engine, the fuel is injected directly into the combustion chamber. The preferred method of injection is known as the common rail system. The system is designed to constantly supply fuel at high pressure to electronically controlled injectors from a shared fuel reservoir. Shown on the screen here is a very simplified diagram of a common rail fuel injector system. The fuel in the reservoir, or common rail as it is known, is maintained at a very high pressure, approximately 1800 bar or 26,000 psi, by a high-pressure fuel pump. In the cylinder heads, fuel injectors, which are really high-speed solenoid valves, inject precise amounts of fuel into the combustion chamber as required. An electronic, computer-controlled dual-channel unit known as a Full Authority Digital Engine Control, or FADEC, uses information obtained from continuously monitoring the operating conditions of the engine to precisely control the injection timing, rail pressure, and the amount of fuel injected into each cylinder. Common rail direct injection offers distinct environmental advantages. Enhanced combustion efficiency leads to reduced exhaust emissions. The system produces quieter, smoother operation over comparable engines with either direct or indirect fuel injection. That is the end of the lesson. The advantages of a low-pressure, continuous flow type of indirect fuel injection system are being displayed on the screen. Review them before moving on. Here are the main points you need to remember about the low-pressure, continuous flow type of indirect fuel injection system. The system is normally equipped with two fuel pumps, which are arranged in parallel. One pump is driven by the engine and the other is powered by an electric motor. The electrical pump is used in case of a malfunction of the engine-driven pump and for engine priming and starting. The fuel metering valve controls the flow of fuel into the engine according to the position of the throttle valve. Thus, fuel flow to the injector nozzles is proportional to airflow. The mixture control valve controls the air-fuel ratio. It can be closed off completely, stopping the engine and acting as the idle cut-off control. The fuel manifold valve is the central point for distributing metered fuel to the engine. A fuel discharge nozzle is located in each cylinder head with its outlet directed towards the inlet port. When you are happy with all these points, move on to review diesel engine fuel injection. In a diesel engine, the fuel is injected directly into the combustion chamber. The preferred method of injection is known as the common rail system. Fuel at high pressure is constantly supplied to electronically controlled injectors from a shared fuel reservoir. The injectors inject precise amounts of fuel into the combustion chamber as required. Injection is controlled by a Full Authority Digital Engine Control, or FADEC.
Rudolf Diesel obtained the German patent for developing the idea for the diesel engine in 1892. An early example is shown here. His objective was to create a very highly efficient engine, and he succeeded by developing an engine with a theoretical thermal efficiency of 75.6%. Gasoline engines had been invented earlier, in 1876, but at that time they were very inefficient. There are two main differences between the gasoline engine and the diesel engine. They are: firstly, while the gasoline engine takes in a mixture of gas and air, compresses it and ignites the mixture with a spark well before top dead center, the diesel engine takes in just air, compresses it, and then injects fuel into the compressed air as the piston reaches top dead center. Thus, it's the heat of the compressed air which ignites the fuel spontaneously, rather than a spark plug. The lack of a spark ignition system in the diesel engine is a big factor in increasing its reliability. Gasoline engines generally use either carburetors, in which the air and fuel is mixed long before the air enters the cylinder, or fuel injection, in which the fuel is injected into the inlet port of each cylinder just prior to the induction stroke. Modern diesel engines, especially those used to power aircraft, use direct fuel injection, which means that the diesel fuel is injected directly into the cylinder. The injector on a diesel engine has to be able to withstand the much higher temperatures and pressures that it experiences inside the cylinder, and yet still deliver the fuel in a fine mist exactly when it's required. The second big difference between a diesel engine and a gasoline engine is in the injection process. As previously stated, most automobile gasoline engines use a fuel injection system or a carburetor rather than direct injection. In an automobile engine, therefore, all of the air-fuel mixture is fed into the cylinder during the induction stroke, and then compressed during the compression stroke. It's this compression of the fuel-air mixture which limits the compression ratio of a gasoline engine, because if the engine compresses the mixture too much, it spontaneously detonates, which is grossly inefficient and can seriously damage the health of the engine. As was stated earlier, the diesel engine compresses only the air. Thus, the compression ratio can be much higher. The higher the compression ratio, the greater the power that is generated from a given quantity of fuel, and the higher the thermal efficiency of the engine. Whereas a gasoline engine compresses the air-fuel mixture at ratios of between 8:1 to 10:1, a diesel engine, which compresses just the air, works at ratios which can range in different engines from 14:1 to as high as 28:1. The higher compression ratio of the diesel engine leads to much higher thermal efficiency. There are problems associated with starting diesel engines from cold, and because of this, some of them utilize glow plugs. Glow plugs are required because the compression achieved in a cold engine may not raise the temperature of the air high enough to ignite the fuel. The glow plug is essentially an electrically heated coil. Once the engine is warm, the glow plugs are no longer needed, and they are turned off. There are two types of glow plug in use, the metal type and the ceramic type. Metal type glow plugs have their heating coils mounted in a heat-resistant alloy tube. Ceramic type glow plugs, which have been employed in diesel engines since 1985, have their heater elements contained in a ceramic material which is made of silicon nitride. Because of this fact, ceramic-type glow plugs have a greater heat resistance and durability. There are two types of fuel injection system which are used in modern light and medium-powered diesel engines. They are the direct fuel injection and the common rail fuel injection systems. We'll look at the direct fuel injection system first. Most light-duty diesel engines use an engine-driven in-line pump to distribute fuel under high pressure to each of the injectors. The injectors are situated in each cylinder head. They are mechanically operated and have spring-loaded poppet valves, so they pop open and spray fuel when the fuel line pressure exceeds a certain limit, typically 4,500 psi. Electronic controls on late model injection pumps regulate injection timing, fuel mixture, and idle speed. The purpose of the fuel injection pump is to deliver an exactly metered amount of fuel under high pressure at the right time to the injector. The injector, unlike those fitted in a gasoline engine which inject the fuel into the intake manifold just before the inlet valve, injects the fuel directly into the combustion chamber, or in some cases a pre-chamber, which is connected to the cylinder. The injection system that delivers fuel to a diesel engine operates at much higher pressure than a gasoline injection system. It can be as high as 17,400 psi for a direct injection system, and up to 23,500 psi for common rail systems, compared to 35 to 90 psi for most gasoline fuel injection systems. Another function of the fuel injection pump is to regulate the timing of the fuel pulses. The timing of the fuel pulses is adjusted in response to engine RPM. Because the vane transfer pump, or low-pressure feed pump, which pulls fuel from the tank to the input of the high-pressure section of the pump, is driven by the engine, at higher engine RPM, its fuel pressure output is higher. These fuel pressure changes are used to either advance or retard the timing. There is also a cold start device, which advances the idle timing manually. A mechanical governor, also fitted to the fuel injection pump, limits the maximum speed of the engine. A magnetically operated valve, or solenoid, opens and shuts off the fuel channel between the feed pump and the metering pump. An air inlet pressure sensor is used to determine the maximum amount of fuel delivered on injection pumps for turbocharged engines. On newer, normally aspirated engines, a similar arrangement is used for altitude compensation. The second type of fuel injection system is the common rail. The common rail fuel injection system is designed to supply constant fuel pressure to electronically controlled injectors from a shared fuel reservoir. This means that the engine fuel supply is not dependent on engine rotational speed. A common rail system is built around four basic components. Firstly, a high-pressure pump with a pressure regulator and an inlet metering valve. Secondly, a rail or fuel feed, which contains a pressurized reserve of fuel. Thirdly, injectors, which inject precise amounts of fuel into the combustion chamber as required. The injectors can be either solenoid-energized valves or operated by piezo crystal. In some circumstances, they can be actuated up to 25 times a second. Finally, an engine control unit, the brain of the system, which precisely controls the flow and timing of the injectors, as well as the rail pressure, while continuously monitoring the operating conditions of the engine. Simply explained, the term common rail refers to the single fuel feed line, from which the individual feeds for each injector are taken, on the common rail direct injection (CDI) engine. Whereas conventional direct injection diesel engines must repeatedly generate fuel pressure for each injection, in the CDI engines the pressure is built up independently of the injection sequence in a high-pressure pump with a pressure regulator and inlet metering valve. This pressure remains permanently available in the fuel line. The common rail, which contains a pressurized reserve of fuel, is upstream of the injectors in the cylinders. It acts as an accumulator, distributing the fuel to the injectors at a constant pressure of up to 1600 bar. Mounted in the cylinder heads, fuel injectors, which are really high-speed solenoid valves, inject precise amounts of fuel into the combustion chamber as required. An electronic driver unit controls each injector's opening and closing. This procedure is regulated by the electronic engine management, the brain of the system, which separately and precisely controls the injection timing, rail pressure, and the amount of fuel injected for each cylinder. It does this by using information obtained from continuously monitoring the operating conditions of the engine. Sensor data from the camshaft and crankshaft provide the foundation for the electronic control unit to adapt the injection pressure precisely to demand. Fuel pressure generation and fuel injection are managed totally independently of each other. This factor is in itself an important advantage of common rail injection over conventional fuel injection systems. Common rail direct injection also offers distinct environmental advantages, with enhanced combustion efficiency leading to reduced exhaust emissions. The system produces quieter, smoother operation over comparable engines with either direct or indirect fuel injection. As early as 1929, the Packard Motor Company of America developed a diesel engine especially intended to power an aircraft. The inaugural flight of the aircraft engine combination, called the Stinson Destroyer, shown here, was from Detroit in Michigan State to Langley Field in the state of Virginia. The aircraft accomplished the trip at an average speed of 85 miles an hour through adverse weather. The straight line distance is 560 miles, but this aircraft, in fighting its way around and through extremely bad weather, travelled approximately 650 miles. The cost of the fuel for the flight in 1929 terms was $4.68. Automotive diesel engines in the past were less powerful than gasoline-fueled aircraft engines, and unfortunately much heavier. Since the 1980s, however, there has been a great evolutionary step forward in the development and production of aviation diesel engines. The common rail principle enables the relationship between the engine's mass and its power to become far more acceptable for aviation usage. As a consequence, due to the adoption of common rail technology and direct fuel injection, and also the use of lighter materials and turbocharger technology, diesel engines offer more advantages to the aviation industry now than they previously could. Two factors allow aircraft diesel engines to be cheaper to operate. First of all, they use the more widely available kerosene jet, Kerojet fuel, which is substantially less expensive than aviation gasoline, and they use considerably less of it. A light aircraft powered by two of these diesel engines can carry 4 passengers at speeds up to 231 miles per hour, while consuming only 1 gallon for every 19 miles travelled. If the engines are set to give maximum economy, then 42 miles to each gallon of fuel in still air can be obtained. That's approximately 9¼ miles to each litre of diesel. This gives diesel-engined aircraft a substantially increased range for a comparable volume of tankage. Secondly, aircraft diesel engines are much more durable than gasoline aircraft engines, so time between overhauls is much greater. Aircraft diesel engines are also safer than gasoline aircraft engines in operation, because of the reduced fire and explosion risk from using Kerojet fuel, and the fact that they use the compression ignition principle. An additional advantage put forward by the promoters of the engine used in the Stinson Detroiter was that it caused negligible radio interference. Of course, this comment was made in the days of fairly primitive airborne radio equipment and very poor interference suppression. However, the fact that compression ignition is used in the diesel engine is still a great advantage. The complications, which are a consequence of having twin magneto-ignition systems, as are fitted to normal gasoline aircraft engines, are removed. There are several different types of aircraft diesel engine presently in production. Amongst these are the Centurion 1.7, shown here, is made by Thielert aircraft engines who are based in Liechtenstein. They took a 4-cylinder engine, which was first used by Mercedes, and totally re-engineered it for use in aircraft. All of the critical parts of the engine were redesigned by Thielert and are now manufactured by them. It's the first modern diesel engine to be fitted to a certified airframe and scheduled for production. The manufacturers say that the engine reduces the cost of flying by 70% compared to gasoline-powered aircraft, based on fuel prices in Germany. Total operating costs for a diesel engine over its lifetime are projected to be an order of magnitude less than that of comparative gasoline-powered engines. The Centurion 1.7 is a liquid-cooled, turbocharged, 4-cylinder, 4-valve inline engine with common rail fuel injection. It develops 135 horsepower and 302.4 pounds-foot of torque. Displacement is 1.68 litres, and it has a compression ratio of 18:1. One of the aircraft to which it's fitted is the Diamond Star DA-40 aircraft, manufactured by Diamond Aircraft Industries. Although rated at only 135 horsepower, the Centurion 1.7 can replace more powerful gasoline engines because it provides more static thrust. Static thrust is that force which is produced when the throttle is advanced. It's a function of engine torque, gear reduction to the propeller, and the pitch of the blades. The Marine Renault's MR200 is now certified and flying in production aircraft in Europe. It's already being fitted to a Cicata TB20, similar to the one shown here, and is available for installation in several American aircraft types. Lycoming's 4-cylinder, horizontally opposed, turbocharged, 4-stroke air-cooled diesel engine is rated at 205 horsepower. This engine has been refined from an existing design which was originally developed in Italy and is now owned by Detroit Diesel. Delta Hawk Incorporated is currently testing a 2-stroke turbo and supercharged, intercooled 4-cylinder, 200 horsepower diesel engine with the cylinders in a 90-degree V configuration. The V-cylinder configuration can be more compact and lighter than opposed configurations. Basic diesel engine operation is as follows. Initially, air is introduced into the cylinder as the piston moves down on the induction stroke. The air is now compressed in the combustion chamber as the crankshaft moves to top dead center. No fuel is yet injected. The compression ratio of the diesel engine is much higher than that of its gasoline equivalent, between 18 or 28 to 1, as opposed to 10 to 1 in high-performance automotive engines. Thus, the extremely high compression causes the air temperature to rise above the flash point of the fuel. When the fuel is then introduced in the combustion chamber, it mixes with the highly compressed and very hot air and combusts spontaneously. The pressure generated by the expansion of the gases as the mixture burns pushes the piston down. The connecting rod transfers the linear energy thus induced to the crankshaft, which translates it into rotary energy. Finally, in a similar manner to the gasoline piston engine, the exhaust valve opens and the piston drives the exhaust gas from the cylinder, and the cycle starts again. In contrast to the gasoline engine, the power output of the diesel engine is actually controlled by the amount of fuel that's introduced into the combustion chamber, while the amount of air remains constant. In the gasoline engine, both the amount of air and the amount of fuel are changed in response to throttle position. The amount of fuel being further altered by the position of the mixture control lever. The mixture control lever of the gasoline engine is required to maintain a balance between the amount of fuel and air being allowed into the combustion chamber in order that a reasonable fuel consumption can be maintained while still keeping the spectre of detonation at bay. Because the fuel is not injected into a diesel engine until the actual required moment of combustion, detonation in this type of engine is not a problem. Diesel engines do not usually operate at the stoichiometric ratio. The stoichiometric ratio is the air-fuel ratio in an engine where all of the fuel and all of the oxygen is burnt completely. If there is more air than is required, a gasoline engine will run weak. If there is more fuel than is required, then the gasoline engine will run rich. Diesel engines always run on a weak mixture, the actual mixture strength depending on the power setting. In the gasoline engine, airflow into the engine is choked by the throttle valve at all times that the engine is not operating at full throttle, which limits its efficiency. With no throttle valve, the diesel engine's intake is fully open all the time, resulting in a much higher efficiency. Most aircraft diesel engines will use regular Kerojet fuel, Jet A, which is a light cut of diesel fuel. Jet A is not a very good lubricant, a problem which has to be especially addressed in the fuel pumps used on gas turbine engines. The fuel pumps used on aircraft diesel engines are no exception. They have to be specially developed for use with Jet A. Although anti-icing additives are used in Jet A, they may not be included in some of the other fuels which can be used in the aviation diesel engine. There is a question, which is still unresolved at the time of writing, as to whether or not to allow anti-icing additives to be used in these other fuels. Anti-icing additives would overcome a tendency which kerosene-like fuels have to absorb more water than does aviation gasoline, but the use of these additives is being curtailed in some countries for environmental reasons. The ability of the fuel to flow in extremely low temperature conditions must also be ensured, and new requirements regarding cetane number must be specified for kerosene jet fuels, which is currently unspecified. The cetane number is a measure of the ignition quality of a diesel fuel. It's often mistaken as a measure of fuel quality. The cetane number is actually a measure of a fuel's ignition delay. This is the time period between the start of injection and start of combustion of the fuel. In a particular diesel engine, higher cetane fuels will have shorter ignition delay periods than lower cetane fuels. Using the appropriate cetane-rated fuel in a diesel engine is critical to developing the power of that engine.